Super. All right. So we're very, very happy to have
I don't hear you at all. I don't know if you can hear me.
So I think they're still having the load shedding issues.
Okay. In the meantime, I think I'm gonna get a charger because I see that my computer is being discharged. So I come back in a couple of minutes. So I'm back.
All right, so Francois, you were so
Oh.
impressive. So impressive that the whole universe shut down.
Okay, well, I gave my entire talk, so I hope you enjoyed it. Look on YouTube.
Oh, very good. Okay, all right, let's try this again. I guess we are still recording.
Are we still recording?
Apparently we are. It'll be a very interesting YouTube experience for those who watched on YouTube. All right, so let's start from the top. So again, super duper thankful for Francois taking the time and the frustration with our South African load shedding to be with us today. He is a CNRS Research Staff in France at Nantes from 2021, and currently the head of the Theory Group of Subatech since 2022. Previously, Francois was CNRS Research Staff at Palaiseau, which is the Ecole polytechnique from 2013 to 2020, and an Annecy from at LAPTH from 2007 to 2012. Prior to that, Francois was a CERN Fellow and a postdoctoral fellow at ECT STAR after receiving his PhD from Subatech in 2001. So, I mean, just a stellar academic record. Any one of us would be deeply envious of that. And Francois is interested in all aspects of hard QCD processes, so photons, weak bosons, Drell-Yan, hadrons, jets, heavy quarks, and all of this in high energy EA, PA, and nucleus collisions. So again, and is also takes part in experimental analyses as an associate theorist for the CMS collaboration. So are you a co-author on these CMS papers?
Indeed, in a few, for five, 6 papers to which I contributed.
Oh, very nice, very nice. So
yeah, it's a nice experience.
Citation count going through the roof.
It helps.
So thank you so much for coming to us virtually to give us this talk, and please take it away when you're ready.
Okay, I'm ready. So thank you, actually, Will and Herbert and all the group of CTMPs. It's a pleasure to be even virtually in South Africa and to meet you virtually, to see that you have a big bunch of students interested in quark-gluon plasma and high energy heavy ion collisions. So I'm very happy to be part of that series. I saw that you've had many great lecturers before me, and so I will try to discuss some aspects of quark-gluon plasma. So I'm sure you know most of it. Other things I'm gonna say, and maybe a few other things that you are less used to. So let me start. So what we're looking after is quark-gluon plasma. So if I try some definition of what quark-gluon plasma or QGP is, I would say it's a deconfined state of matter in which you have quarks and gluons, which are in a bath in a thermal equilibrium. And we believe it existed in the early universe. So typically it's microseconds scale. And it's also produced in the first few Fermi overseas in the high energy heavy ion collisions. And now there's even some debate whether it exists even in the core of massive neutron stars. And for that, we have nice gravitational wave data that seem to indicate that maybe we have some QGP even there. So it's a pretty hot cosmic soup. And this idea of quark-gluon plasma is almost as old as QCD itself. So it was formulated in the 70s, and it directly follows from the Parton model, and thanks to the asymptotic freedom, which I'm going to discuss briefly in a few slides, we believe that there could be some weakly coupled plasma if temperature is very, very large, or if the chemical potential, so say the baryon asymmetry in the plasma is very large as well. And of course, it addresses the question, the big question of confinement in QCD. So this is a cartoon that you have seen probably before, which shows the evolution of the universe. And we start with a Big Bang, and we have an epoch of inflation. And then we start to do some LHC physics to reach these scales at the weak scale, let's say 100 GeV, with LHC proton-proton collisions. And that at RIC and in heavy-ion collisions, that's where we are here. So we are more interested into the QCD phase transition with a temperature of the order of 100 MeV. So this corresponds to time scales, as I said, say from 1 to say 100 microseconds. And then for the first few minutes, and then we start to have some of course, confined hadrons and then atomic nuclei, atoms, and then the decoupling of light. And that's more or less where we are today. So speaking of today, so I will discuss first some aspects of QCD and how QCD led to the concept of QGP, quark-gluon plasma. I will discuss briefly some QCD thermodynamics, and then I will switch to high energy heavy-ion collisions, mentioning some facilities and the signatures of QGP formation. And in the last but main part of the talk, I will discuss the production of hard probes on how to probe quark-gluon plasma with hard QCD processes. I will mention the physics of radiative energy loss and its consequences in the experiment, namely the quenching of hadron spectra and jet quenching in the very last part of the talk. So let's start with a QCD. That's what we're doing after all. So it's the gauge theory of the strong interactions, so between the quarks and gluons, and it's based on a symmetry group SU&C, when number of colors is 3, and it's a non-abelian theory. So meaning that the bosons carry themselves some charges, gluons are charged, and this is very unlike QED, in which the photons are not electrically charged, of course. So I will mention sometimes the coupling or the strong coupling constant, which is G²/4π. And well, I will discuss asymptotic freedom, but okay, it's of the order of 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ And I will come to that. And about the field contents, well, we have quarks, we have NF flavors, so principal NF equals 6, but in our case, I will mention sometimes that NF is 3, the number of active light quarks in quark plasma, times NC, and of course the 8 gluons in QCD. So I put here some indicative masses for the quarks, but be careful when you see some quark masses, because these are not asymptotic particles. These are that's the problem of confinement. So it's very hard to define a mass of an asymptotic particle. So I mentioned these two main aspects of QCD: asymptotic freedom and confinement. So let me start with asymptotic freedom, which gave this Nobel Prize in almost 20 years ago to Gors, Palaiseau, and Wilczek, who computed the gluon self-energy. So principle, you will have to include some quark loops and gluon loops. So it's quite a heroic calculation at the time, and this led to the calculation of alpha S, so the coupling constant, with respect to your resolution scale, to your energy scale. So can define what we call the beta function, which is how the coupling would change with the resolution scale. And it turned out to be negative because of precisely of the gluon loops. And this is key because it means that if you come with a very, very large energy scale or very, very small distance scale, if you wish, the coupling goes to 0, and then we have a perfectly weakly coupled theory, which give rise to the use of perturbative techniques and perturbative QCD in that context. So it was of course, a key observation, and this is the translation in terms of data. And you see beautifully that indeed, when you try to extract alpha S as a function of the resolution scale, you see that it decreases slowly but surely, and you see that how beautifully the data come exactly on that one loop expression here. So it has been tested with a very high precision. Many different observables like jets and Drell-Yan, tau decays, and others. And in heaven physics, as I said, I mean, the natural scale is the temperature. So if the temperature is very, very large as compared to lambda QCD, then the coupling is small. So you could expect a weakly coupled system at very large temperature. On the other side, if you go to very large distances, well, things are more complicated because, as I said, quarks and gluons is not what you observe in your detector. These are not asymptotic states. You observe hadrons. And this is because quarks and gluons, they cannot propagate over large distances. So typical scale is 1 over lambda QCD, which is 1 Fermi. This is the typical hadron radii that you could expect. So color charges are trapped in these states called hadrons, be it mesons or baryons, or now we have some exotic states that have been measured at the LHC. And I want to emphasize that the origin of confinement is still unknown. This is merely an observation. There's a lot of theoretical progress on what actually causes color confinement, and it's still not clear, and so it's still an open question. And you could see a way to see this confinement appearing is to compute, say, the potential between 2 very heavy charges, between 2 heavy quarks. And this is the plot that you see here, in which you have this potential at very small distance, which looks like Coulomb behavior, just like you would have in QED at very, very small distances. But when you start to go to larger distances, then you see this rising potential. This is in pure gauge. We don't have light quarks, so the potential would go on. And it means that whenever you want to separate these 2 heavy charges, then you have to pay a price, and which is called string tension. So each time you want to separate them from an extra Fermi, you have to pay this price of 1 GeV. So it has been parameterized quite oftenly as this Coulombic part and this linear part at large distance. So it's a way to see this kind of confinement, even though, of course, it does not give any explanation on the origin of that. So as I said, we have QCD, we have the Parton model, we have the asymptotic freedom, and from all this, there are a few papers that appeared in the middle of the 70s, which suggested that all this leads to the concept of quark-gluon plasma. And this is one of the papers that I mentioned here by Collins and Perry in 75, in which they mentioned that, well, given the fact that we have some particles, some hadrons, which have some typical size of 1 Fermi, and we know they are made of quarks and gluons, well, then if the density is so large, at some point that they should overlap, and there should be some phase change, maybe not a phase transition, but at least something that goes from the hadronic world to quark or quark-gluon soup. And this is illustrated here, in which start to compress your say your hadron gas, and at some point you cannot say that which quarks belongs to which hadron, and then they start to be free, at least as long as the density is large. So this even the phase diagram of QCD, in which you have on the 2 axes the baryonic density and the temperature, as was guessed in this paper in 75, and you see that actually, of course, now it's much more complex, but still this structure survived. So we are here. This is a nucleus with a, say, 0.17 nucleon per cubic Fermi. And then if we start to heat a little bit, then we'll have all the hadrons coming out, so like pions and kaons, and depending on the temperature. But then at some point you may reach a boundary or another phase, let's say, in which you have quark-gluon plasma. So typically at RIC and LHC, I will come to that, we are moving along this axis. So the number of baryons and the number of antibaryons is very close. It's almost symmetric at very high energy, but the temperature is very high. So this is what we do in heavy ion experiments. And if we start to lower the coordination energy, maybe we'll start to increase the number of quarks with respect to the entire quarks, and we'll start to probe another region of the QCD phase diagram. But in any case, yes, in this region, that's what we want to go in these high energy event collisions. Okay, so with that being said, it would be interesting to compute maybe the easiest thing we could think of is typically the energy density of a boson gas or a fermion gas. And if you do that, well, you integrate over the, of course, the distributions, Bose-Einstein or Fermi-Dirac distributions. And since we have here only one scale, which is the temperature, then the energy density is just by dimensional arguments, scales like T⁴, and with some coefficients in front, which would be different whether we have fermions or bosons, times the typical degeneracy factor. So how many different states you could expect in your plasma. So if I do that for a pion gas or quark-gluon plasma, well, pions are bosons, so you'd have expect that. And in quark-gluon plasma, you have fermions and bosons. So in principle, you have this. And if we start to count the number of states, well, you have 3 different pions. But where it comes to be very interesting is when you start to count the number of gluons and quarks. Of course, you have many more, precisely because of color. So you have 8 gluons times the spin. So you could expect G of glue of 16. And for the number of quarks, as I said, well, there's some ambiguity here in terms of a number of flavors. At very, very low temperature, maybe you would not have any strange quarks floating around. And at very, very high energy, you could have to start to have some thermal production of charm or even bottom if you wish. But let's say that NF is say 2 or 3, and you come up with some factor here like this. So if I plug these numbers in the estimate before, well, what is interesting is that you start from a number times 3, and for quark-gluon plasma, you have something which is 10 times larger. So there's a very big jump in principle of energy density or other thermodynamical quantities like say entropy or pressure from say a hadron gas or pion gas to the quark-gluon plasma. And in between, it's of course these are quite asymptotic estimates, and in between it's difficult to compute that, and we can do that using lattice QCD. So I will say just a few words on lattice QCD, of which I'm certainly not an expert. The idea is that you can compute some actions if you discretize your space-time. So it was formulated by Wilson, and then we start to have some of the first Monte Carlo studies in the 1980s. And now, of course, with the latest supercomputers, we have become increasingly more accurate. And this is just a cartoon of some discretized spacetime. Of course, all your results will depend on the size of your grids, of your spacetime and the lattice spacing. So it's quite subtle how to compute observables on the lattice. But here you have a nice example of the hadron mass spectrum. So of course we have to put some ingredients in your calculation, some scales, and these are say typically the pion or the kaon mass. But from that you can really compute all the other states. So which is quite impressive. In the proton mass has been determined with great accuracy recently. So on the lattice, we can compute QCD thermodynamics. So now it's a bit different. Now we have a temperature or a finite chemical potential. So if we stare at 0 chemical potential, so the number of quarks and the number of anti-quarks is the same, well, we can vary the temperature. So we can compute in principle the equation of state. So typically how pressure or entropy would vary with the temperature, how those are related with one another. And you can compute other things like the heavy quark potential, which I showed you before, but now you can do that at finite temperature, or you can compute also meson spectral function, which is interesting as well. If you want to explore the phase diagram, at finite chemical potential, then it becomes to be very, very problematic, because you have some what we call the sign problem, that we have to integrate over a rapidly oscillating function, and this is notoriously difficult. So whenever mu becomes of the order of t, then you may no longer use lattice QCD, and you have to rely on other say on models if you want to have some expectations. But still, that being said, so here you have a nice example, a famous example of this equation of state as a function of the temperature, and you see that for the pressure, the energy density, and the entropy. So as you could expect, you have some rapid change, say around some critical value. So I say around, it's not very precise, because after all, there's maybe no real phase transition per se at zero chemical potentials. It's just a rapid change, and of course it's hard to define some critical temperature when we don't have a phase transition, but it should be of the order of 150 MeV. And you see this change from the pion gas to the Quark-gluon plasma. Maybe you could have some first order phase transition. I will come to that when the chemical potential is finite. But if you look carefully at that plot, you see that we are still very far away from what we computed before, which is the non-interacting limit, in which you have a perfectly weakly coupled system. So you see that you tend to see that, well, maybe the medium is still strongly coupled, or at least not weakly coupled, even though the temperature is very large. And this is also because you have a large occupation number. So it's not just alpha S which matters, but it's also times the number of the occupation numbers that you have. So if you have a large number of particles around, even if the coupling is quite small, you may have some strongly coupled physics underlying, and you will see that that's what we observe in the experiment. So I was mentioning the structure of the phase transition in QCD as computed on the lattice, and you see on that plot, you see the mass of the U and Ds, which is assumed in the calculation, and the strange quark here on that axis. So if those are sent to infinity, you are pure gauge theory, just only gluons around, and in the Carroll limit, in which all the masses are set to zero, we are on that corner. And the physical point in which you have very small, very light UND quarks and slightly more massive strange quark, the physical point may be here. Of course, it's just indicative and illustrative. But you see that in that region, we have a crossover. There is no real transition here, and with a transition temperature of the order of 150 MeV. While in those other theories, say, you could expect in principle first order. But this is at zero chemical potential. So who knows what happens when the chemical potential is finite on, say, on the third axis. And maybe at some point you will reach a new boundary, a critical point in which you start to have some first order phase transition. So it's not clear at the moment whether there is still such a critical point in the QCD phase diagram. Okay, so now let me switch a bit more towards the experimental world. So we want to produce that Quark-gluon plasma. So we will have to heat matter above 150 MeV. So if you translate that, this is our natural units, of course. But if you multiply by the Boltzmann constant, you would get some temperature of the order, or if you divide by that, you would have some temperature of the order of 2000 billion degrees. So we can heat matter just like that. So we smash heavy particles, so heavy ions. So typically a heavy ion could be a lead or a gold nucleus with a 200 nucleons. In that sense, it's a lot of matter as compared to a proton at high energy. So typically either at RIC or at LHC, these are the two colliders that we currently have. So Rick has studied more than 20 years ago in Brookhaven National Lab in the US. So we had lots of collisions in gold, and copper, even copper gold, and even more systems now, I think, on a variety of collision energy. So the top energy was used a lot, 200 GeV, but also to scan the QCD phase diagram, people managed to do collisions from, say, 10 to 200 GeV. And there were four big experiments. And the LHC since 2010, so we had mostly lead-lead collisions, a little bit of xenon collisions, and the typical energies are, say, from 2 to 5 TeV. And there was one big experiment called ALICE, the Large Ion Collider experiment, which was really dedicated to heavy ion physics. But the good thing is that LAPTH and CMS managed also to perform wonderful measurements, even in heavy ion collisions. And now the LHCb experiment is trying to do some heavy ion collisions. Now they managed to to do measurements at least in peripheral heavy ion collisions. So, but it's going to change in the next few years. Okay, this is a picture of the REC facility in the US with some injection. So it used to be, of course, also a facility, the HGS in the 80s, and now it serves as an injector to RIC with the different experiments. And RIC was famous. I will show some data from RIC, and it was famous, and it is still famous for the discovery of jet quenching. This is really the first time that we saw jet quenching, or hadron quenching, I should say. And also famous for the strong flow, strong azimuthal anisotropy that was measured in these collisions. And I will also come back to that later on. LHC, this is another picture where you see Geneva Lake and Mont Blanc here, and you have this huge collider, and CERN is over there. And well, it's famous for many things, but obviously because of the larger collision energy, we get to larger energy density and larger even temperatures, and also many new measurements. Maybe that's what is the most important thing, is that since you have a larger phase space, larger collision energy, we can measure many more particles that were not accessible at REC energy. So let me come to data then. So the very first measurement that appears when you switch on your accelerator is the number of particles that you see in your detector. It's quite an easy measurement and fast. You don't need to have lots of collisions to produce this very precise data, in which here you have the rapidity distribution of charged particles, either at so here at REC energy at 20 GeV and 200 GeV, and now we have some LHC data at 276, and we have, of course, even at 5 TeV now. And the first thing that you see, obviously, is the plateau, or almost a plateau. It's a log scale, but you see that it's fairly flat in at mid rapidity, and this is what you would expect from the longitudinal expansion of your medium. So you have the colliding pancakes, and then you produce your medium, and it expands mostly longitudinally, and of course a bit also transversely. And because of this longitudinal expansion, this led Bjorken to propose a simple picture, and which leads to this rapidity plateau. And thanks to this plateau, you can extract the typical energy density that was in the early times of the collision, which is, of course, a quantity that you want to access. So if in this plot, now there's experimentalists by Phoenix, they collected all the data that they have on the RIC beam energy scans, say from 10 to 200 GeV, and then they added the LHC point, and you see that you have the Bjorken energy density as a function of root S. You have a nice parallel behavior, beautiful, and that LHC, not even top LHC energy, you have something like 14 GeV per cubic Fermi. It's of course an order of magnitude, estimate, but still it's a large number, of course, larger than at RIC because of the larger root S. So it's typically 2 to 3 times larger than at Rick. And what is interesting is that the energy density is much that above what you could expect from lattice QCD for this energy density, critical energy density for the transition. So it seems that even though it's a bit indirect, that indeed such large energy densities cannot be reached with a hadron gas, but it has to be quark-gluon plasma. So at the same time, even though I mentioned this factor of 2 from RIG to LHC, you see that it's not that big of a change. I mean, if you remember that the energy density goes like T to the 4th, and it's not such a big change in terms of temperature when you go from RIG to LHC. So the quark-gluon plasma is almost the same, I would say, but at least properties will not change that much, but the rates of other particles, what I would call the rare probes or the hard probes, would change a lot. And this is, I think, the most important thing to keep in mind, that at LHC, maybe the medium is a bit, of course, hotter and denser. It will live a bit longer, but it's really the rates of jets and weak bosons or Higgs bosons, if you wish, that would increase a lot from one energy to another. So this is really the big asset of LHC. So we produce the quark-gluon plasma, and it would live not long. It would live a few Fermi over C. So in terms of seconds, it should be something like 10 to the minus 22 or so. So it's impossible to measure and to see it directly, obviously. So so we need some what I would call some fossil measurements, which we call signatures. While fossil, while this analogy with the dinosaurs, well, because we want to see some signals in our detectors that tells us that indeed quark-gluon plasma has been formed, even though of course we come long after the extension of that quark-gluon plasma, and it's in that sense it's I think it's a good analogy that you see fossils, and from that with some theorist friends you can maybe try to guess what was the life, say 200 billion years ago. So it's a bit the same, if you wish. So we measure long after the quark-gluon plasma, and well, we will start to guess what was the temperature of viscosity of quark-gluon plasma long before. So there were many signatures that were proposed, mostly in the 80s, in the 90s. So here, this is a list. I will not have time to cover that all. But let me mention the elliptic flow that I will discuss, and the jet quenching. On top of that, you have some other beautiful signatures that were seen in the experiment, like quark-gluon suppression, the fact that the J size or the epsilons would dissolve in a quark-gluon plasma due to the bi-screening, or you have some thermal radiation. So you have some extra photon production at transverse momenta of the order of the temperature. You can have even an increase in the number of strange quarks in the plasma due to chiral symmetry restoration. So the list is not exhaustive. So different experiments can be better or than others doing this or that measurement. And after all, I mean, in the end, the big picture is really from the combination of all these that we start to guess what is this medium that we produce in these collisions. So typically there are two strategies. Sometimes we hear, oh, looking on soft probes or hard probes, and basically these are the two strategies. Either you measure quark-gluon plasma. So as I said, you cannot measure it, but you see the remnants of that quark-gluon plasma, but you really measure the particles that came from that quark-gluon plasma. And typically these have transverse momenta of the order of the medium temperature. So say 1 GeV, a few GeVs if you wish. And there are many measurements that you can do. I mean, I mentioned already the single particle d and eta distribution. You can look at two particle correlations of rather soft particles. You can measure thermal radiation, as I said, and you can also look at anisotropies, which I'm going to discuss in a minute. And from this typical soft particle progression, you would rely on some framework which is typically relativistic fluid dynamics. So I know that you had great lectures before by George, I think, on that. Basically, it assumes that there is some local thermodynamical equilibriums, so that the mean free path of particles in the medium is very, very small. So we assume something which is quite strongly coupled, and at least in this ideal case, and it's very, very predictive. So a nice measurement that was proposed a long time ago is to look at the azimuthal anisotropies in heavy collision. So here on that cartoon, you have the two nuclei that cross, and you have this overlap region, which is of an almond shape. So you can see that it's squeezed in some sense, and the particles want to escape. So there is in other words, there is some pressure gradient which is a bit much stronger along this, what we call the reaction plane, even though we cannot really measure that. But in principle, they would have a preference to flow along phi equals 0 or phi equal pi rather than at phi by half or 3 pi half. Okay, so this spatial anisotropy, because of interaction, would lead to some momentum anisotropy, which you can measure easily experimentally. And these are characterized by some coefficients. So experimentalists would measure the phi distributions, and they would do some Fourier decomposition. And then the first few coefficients can be guessed and would give a hint on the pressure gradient, and so on the validity of the relativistic hydro, and on the viscosity parameters, and so on. So these are some measurements that were done at RIG and at LHC. So you see one such example of what we call the V2, the first this coefficient, as a function of the collision centrality. So here you have very, very central collision. So when it's B equals 0, then it's so symmetric that, of course, there is no anisotropy that you could expect. So V2 goes to 0, but that in some mid-peripheral, mid-central collisions, you have some non-negligible V2, which is of the order of 5 to almost 10%, which is quite a big number. And here you see these same measurement, and now as a function of the transverse momentum of the particles that you measure. And while you see some different data, because it's a subtle measurement on how you do that, how you get rid of some processes that have nothing to do with the pressure gradient. So there are different experimental techniques, but okay, that's it gives you an idea on the experimental uncertainty, if you wish. And you see that there are some relativistic hydrodynamical calculations, and which reproduces well the trends. I will not discuss the details, but okay, the trend is clearly reproduced, and then depending on the viscosity that you put into your hydrodynamical calculation, you may reproduce better or not the data. So the data really is some kind of measure of the viscosity of the medium. So it's quite exciting. And what was even more exciting is that well, almost ideal hydro, so with a 0 viscosity, which is this parameter eta, even with a 0 viscosity, you almost reproduce perfectly the data. So it seems that this is a very perfect fluid. Of course, nothing is so perfect, but at least this eta over S ratio, which is dimensionless, is something small. Say it's much smaller than 1 for sure. And the LHC measurement confirmed that in the quark-gluon plasma at RIG and at LHC has a very low viscosity. So if you remember, viscosity is related to the fact that well, we have some departure from ideal hydro. So if the mean free path is very, very, very small, so we have very strong interaction, viscosity is very, very small. So having a small eta over S ratio means that we have strong interaction here. So very far away from what I told you at the beginning, the ideal world of a weakly coupled Quark-gluon system. And so that was what we call the paradigm of the perfect fluid that was discovered at RIG. It was exciting or shock at the same time to realize that the medium is so fluid. So quark-gluon plasma is perhaps say 5 to 10 times less viscous than say superfluid helium. Here you have a collection of different materials, quark-gluon plasma, and so superfluid helium and water as a function of the temperature and the critical temperature for the transition. So have a minimal near the phase transition. But you see, if you look on the vertical axis, you see that well, of course there is some uncertainty here, but really the viscosity is very small at RIC and LHC. And it was proposed that in some strongly coupled theories that well, it makes sense in the strongly coupled theory to have a very small viscosity from what I said. And well, so there was some bound that was conjectured to be whatever 4 pi for this ratio. And well, it seems that we are fairly close, at least from phenomenological estimates of that 1/4 pi scale. Okay, so that was a strategy on the soft probes. As I said, you measure the soft particles that come from the soft quark-gluons, quarks and gluons in your plasma. There's another strategy which myself was more interested in, is to look at rather external probes. So there's no such thing as an external probe. And of course, you would like to have your quark-gluon plasma that is at rest and a large volume, and then you would do some DIS experiment on that. That would be perfect. But from the lifetime of the quark-gluon plasma, it's impossible. So this very same collisions, very same heavy collision would both produce the quark-gluon plasma and produce sometimes some hard particles. Hard particles meaning either with a very large mass or with a very large transverse momentum, much larger than the GV scale or the temperature scale of your medium. So we can think of heavy quarks naturally for heavy particles. Now even top quarks have been measured at the LHC in LAPTH collisions or quarkonia. And we can also think of, as I said, I mean, very large rapid particles that go through the medium, so with a very large transverse momentum. So these more like with a tomographic picture in mind that you have a medium and then you start to scatter very rapid particles in that medium and you see what comes out, and you try to guess what was the medium about. So in these hard processes, of course, the natural theoretical framework is probably QCD, but of course PQCD which would be embedded ideally into some soft hydro medium, because you still have the quark-gluon plasma that you want to study. So it's not just PQCD as you would expect maybe in some proton-proton collisions. Okay, so why hard processes? I want to motivate a little bit that. I'm looking at the time. I think I still have a little bit of time. So we're looking to large transverse momentum or large momentum transfers. So we have a great variety of particles of hard processes, or either with bosons and photons and high PT hadrons, and we can study them in QCD thanks to asymptotic freedom. Because of the large scale, Q is much larger than lambda QCD. We can apply PQCD. We can compare it to PP collisions. So it's quite good. I mean, you have in principle a good reference. But the caveat is that for some cases, things are less understood. And here I have in mind the hadrons. So as soon as you start to deal with hadrons, it's more complicated in PQCD, unlike say jets and heavy quark jets or weak bosons. So keep that in mind, obviously. And so, as I said, I mean, we can produce these hard processes both in PP collisions, in which, in principle, you will not have a quark-gluon plasma which is produced, at least in some, say, minimum bias PP collisions, and you have these hard processes in nucleon-nucleon collisions inside your heavy ion collision. So the natural measurement that you could think of is RA or RAB, in which you compare the rates in the heavy ion collisions, AB collisions, over that in PP collision, and you have to normalize this observable by Ecole, which is the typical number of binary nucleon collision that you would expect, since this will naturally increase the rates of hard processes of course, in AB collisions as compared to PP collisions. But say, suppose that AB collision is just a superposition of A times A nucleons times B nucleons collisions, you would expect RA to be close to 1. And that's not what you observe. So as I said, we can use factorization. We can use perturbative QCD. So in a nutshell, when the hardness of your collision is very, very large as compared to the other scales, say the non-perturbative scale of QCD is 200 MeV. When Q is large, then you can compute this cross-section in PP collisions as just an incoherent sum of partonic collisions, IJ. Okay, so you pick a parton A, pick a parton B in your two hadrons, and then you can really compute Feynman diagrams and compute the final state. So it's nice because you have some predictive power, because these parton distributions in your hadrons are known from other experiments like DIS experiments. And they are supposed to be universal. So you can, in principle, apply them in PP collisions. Maybe you could even apply them in heavy ion collisions as well. And as I said, the short distance part, so the scattering of your two partons, is calculable in PQCD. And I mentioned that it is an approximation because when Q is not that large, then you may have some terms that would spoil a bit this picture. And this is a bit of a teaser for next week, in which I'm gonna be interested in some processes that would actually spoil this nice factorization picture in PP collisions. So the idea again is to look at the effects of the medium that is there on the rates of hard processes. So you can distinguish between colored probes like jets and electrochromic probes like prompt photons. So some should be modified like jets because they carry color, and the weak probes should not be modified because they do not carry color. So the mean free path in the plasma is much larger than the plasma size. So among these hard processes, the most famous maybe is jet quenching, and jet quenching would be in the minimal formulation, say the suppression of jets in AA collisions with respect to PP collisions, and the physical origin of that is due to pattern energy loss. So you have this nice cartoon in which you have two protons colliding and you produce two back-to-back jets. They are never back-to-back in practice because it's just a leading order picture, and so you have some radiation all over the place, but it's say pretty well balanced. While in heavy ion collisions, it's more imbalanced because you have maybe one jet that escapes and the other jet has suffered a lot and loses a lot of energy. So it will increase the imbalance between the two jets. So that's the basic idea, and that was observed very spectacularly at LHC. So this idea was actually due to Burken and a long time ago, in '82, in which he mentioned in that unpublished paper, you can look at that paper, it's available on the Inspire, in which he mentioned that while it was in the elastic scattering in that case, not radiative energy loss, but he supposed that indeed quarks and gluons would lose some energy, and even predicts that one jet could be escaping without any harm, while the other being absorbed in the medium. So everything is there, but you still have to do the calculation. So this has triggered a lot of theoretical activity, looking at how much. So the basic question is how much a charged particle lose energy when going through a medium. So it's quite a general question, of course, in physics, not only in quark-gluon plasma, but in QCD, it becomes quite involved because of the of the charged gluons themselves that can rescatter on the in the medium. So there were many calculations, mostly in the 1990s and 2000s, on how to compute the rates, the spectra of gluons, which are induced by all this rescattering. Okay, so you can either assume that there is a very large number of scattering centers or a very few number of scattering centers, and depending on that, you may have some different frameworks to compute this gluon radiation. So it's a very active field. As I mentioned at the very beginning, the focus was on the energy loss of a single hard parton, which is the simplest case. So you just shoot a quark, you shoot a gluon in your plasma, and then you compute how much this particle has radiated energy. So with the different formalisms that I mentioned, and this picture of one single particle is naturally suited to describe high PT hadron production. So if you say you measure experimentally a very high PT hadron, then for sure the hadron would be a nice proxy of your initial hard parton, and I will try to convince you in the next few slides. While more recently, in the last 10-15 years, the focus was more on the energy loss of a multi-particle final state. So it's even more exciting in that sense. You have many particles floating around due to the jet evolution, and how this complex system will lose energy is quite difficult to answer this question. But yeah, there are many attempts to model the full shower in QCD. So really the picture of single particle to a more complex system. And this was also triggered by the experimental and theoretical developments on how to reconstruct jets in a dense environment. For a long time, people thought it would be impossible because you have so large number of particles around, so large what we call underlying event. That is hard to do, but still they managed to do that, and now to start to look inside jets. I will come to that. So just a few dates. I mean, on top of these theoretical developments on the experimental side. Well, in 2001 is really the year in which people said, well, okay, we have some hints of jet quenching with a quotation mark, because it was more of the quenching of hadrons at RIC. And after the LHC came, we had the first measurements of jets, so 2010. And now we start to look at, as I said, inside jets in heaven collisions. And that was 5-6 years ago. Okay, so we start to really access the physics of induced intrajet radiation. So a complex system going through a complex medium. And we measure that, and some people do calculations of that. This is an example of a CMS measurement in which you see two very imbalanced jets. Again, remember that in PP collisions, you could have such events like that. Nothing prevents you in QCD to have one jet that is radiating a lot and the other much less. So, but we have many more events like these in heaven collisions than in PP collisions, in which typically we would interpret this as one jet being really absorbed in the medium or radiating a lot, and while the other has escaped without any problem. Okay, so just to give you a flavor on the different regimes that play a role. Well, it's mostly a comparison of two length scales. So when you shoot a particle and well, you have some medium length L, capital L, and you know that there is some pattern mean free path, which is related to the interaction cross section and the medium density. So in that cartoon, the mean free path would be the distance between said two scattering centers, and the L would be the entire length here. Okay, so depending on the gluon formation time, so the gluons need some time to be produced. So this is the other scale, which is typically related to the omega over Kepler squared. It's just rough estimate for this gluon formation time. So depending on the value of on where you sit in this omega Kepler squared plane, if you wish, well, you may have some different regimes. So if the formation time is very small as compared to the distance between two scattering centers, between the mean free path, then it means that all your radiation in a big say big medium is just very simple, because all these scattering centers are independent from each other, because this gluon formation time is very small. So it's produced and then it's lost somewhere. So there is no interference between different scattering centers. So we have just Ecole scattering centers, where L would be the total length of the medium over the mean free path. Okay. Now it starts to be interesting when the formation time is larger than the mean free path, and when it's larger, then the gluons would see different scattering centers at once, and all these scattering centers would act as just as one single radiator. So if the formation time is here on this blob, this is the typical formation time of that gluon, you would see those 4 scattering centers as just one scattering center. So in principle, you expect less radiation because of this quantum mechanical effect called LPM effect. And here it's really the group of formation time over lambda scattering centers that will play a role. And because the formation time depends on the gluon energy, you will see that there is a suppression as a function of the gluon energy as compared to the what we call the Bethe-Heitler regime, which is completely independent. And finally, there's another regime when the formation time is much larger than the whole length. And then in that case, well, there's just one big scattering center for at least as viewed from for the gluon. And it will still have some radiation, but you see that there is no difference with say between the thick medium and a large medium, because there's just one scattering center. So there is no medium-induced radiation. You would have the same radiation, say in PP and in A collision. So in principle, it will be strongly suppressed at large omega. So when you translate these regime, but what is most important is really the physical regimes that I mentioned. Well, when you translate that into numbers for your induced gluon radiation, you see that this Bethe-Heitler is, as I said, proportional to the medium size over the lambda, so the number of really actual gluons in your Quark-gluon plasma. While for the LPM, you have a suppression by 1 of square root of gluon energy. And on this log sketch, you have that you start from something which is constant to a suppression, which we call the LPM radiation. And for the finally, a fully coherent regime at very large omega, it drops even much faster. So in the end, if you integrate all that to know what is the typical energy loss suffered by a particle going through the plasma, you will see that it's typically this regime LPM which really matters. So the average energy loss, even though we could discuss on the relevance of averages for phenomenology, but at least it's dominated by gluon formation time of the order of L. So parametrically, we expect some delta A, which is proportional to these scales, where Q hat will gives you an idea on the scattering property of your medium. And this is the medium length squared I would expect. And of course, some ratio, which depends on the color charge of your particle, be it for quarks or gluons. And I would be quick here, but of course, because of the medium is expanding, we have no such thing as a static medium, as I said before. So Q hat in principle depends on the proper time, because it's related to the particle multiplicity. And so in principle, you would lose maybe some power here for the average energy loss, just because of the cooling of your Quark-gluon plasma. And you may also have some mass effects when the particle, the quark is not considered as massless, but has a mass. while you may have some less radiation in that case, which we call the dead cone effect, which has been seen in E plus, E minus in the vacuum, but which we could expect as well in quark-gluon plasma. Before I go on, would you tell me how much time I have, because we started late. I've still some things to say, but let me know.
Yeah, I think maximum would be 4 p.m. on my side, which is, I think should be plenty.
Yeah, don't worry. Maybe I have 10 more minutes. I still want to save some time for questions. So if I speak 10 more minutes, is it okay?
Sounds wonderful. Yeah.
I used too many slides. Sorry for that. Okay. So sorry if I rushed a little. Okay, so now after this small theoretical digression on how to compute and what are the regimes, so let me show you some data. So here you have some RAA. So this suppression of hadrons at Rick. So that was really their discovery. I think these few points up to 7 GeV. I remember when it was first announced, it was quite exciting to see that RAA is not one. It is one if you measure, say, photons. Photons are electrically neutral and they are not suppressed at all. But and in d-gold collisions, in which in principle you have a lesser density than in gold-gold collisions, you also have something close to one. So it seems that indeed there is something going on, and it is quite natural to interpret this as pattern energy loss. And I want to discuss a bit more physically how to understand these data, and especially LHC data, by taking a very simple energy loss model, which I discussed in some papers. And so I just wanted to share with you a little bit because it's very simple and easy to understand. Well, if you want to measure to calculate, say, the spectrum of particles in your in AA collisions, it could be simply as just a PP cross section. So with you can measure, or you can compute in perturbative QCD, but with a shift in the energy loss. Okay, due to the energy loss, the initial transverse momentum was not PT, the one that you measured, but PT plus something, plus the energy loss, and you have, of course, to integrate over the probability to have this single energy loss epsilon. There's a small z here because you have to remember that hadrons take only a small fraction or some fraction of the pattern energy. Okay, and in the formalisms that I discussed before, the BDMPS and GLV and so on, we can compute this quenching weight, and it is characterized by one scale, which can be related to the first moment of that, of course, of that distribution. So things become quite simple, especially if you remember that at very large PT in PP collisions, there is no other scale than PT. So the PP cross-section has to go like a power law, and there's no other scale. So it's 1 over PT in principle to the power 4, just from dimensional reasons. Then, of course, there are many things that would complicate a little bit the picture, and it's not exactly 4 that you see in data, maybe 5 or 6, but it's very simple. At least it's a nice parallel that you see. So if you have this simple formula for this energy loss, and with this parallel, then you can compute what I call the RA, which is just a convolution of the quenching weight of that energy loss probability distribution times this factor, which comes from this parallel behavior of the PP cross section. So what you see that in principle, it should depend on PT and on the average energy loss, but in that simple model, at least, it scales like PT over the pattern energy loss. It's just it depends only on one variable instead of 2, and this you can compute quite easily. The only thing that you cannot compute easily is this average energy loss, which in the next slides I will take as a free parameter determined from data. Okay, so you have a simple scaling property in principle, which is even better in a sense that if you remember that n was the parallel in PP cross section, you can even exponentiate that, and it would even scale, have even better scaling here, which is here shown here. So it took different values of n, and in my calculation, I said PT over n times average energy loss, another scale here. And you have some universal curve for, say, for either BDMPS quenching weight or GLV quenching weight and so on. And how it translates in the data is shown here. So what it takes is say, okay, let's take all the data that we have at RIC, at LHC, and all centralities. Of course, for all these collisions, different collision systems would have different average pattern energy loss, but let's be very agnostic and say, okay, I will fit the data with just my single curve, and each time I will have some values of epsilon. So when I scale that, I see that all the data indeed show this nice scaling property. So whatever your collision is, the area has the same behavior as a function of PT. So it's a good sign. And not only there is a scaling, but also the default model reproduces well, captures well this trend. So it looks like, even though it's very simple, at least the idea of a single pattern energy loss in QGP can explain it all. And here is just an example of all the scales that I obtained from feeding the data. So it's interesting in itself. So when you go to peripheral collisions, you have much less energy loss. And if you go to more central collisions, you have larger energy loss. And this is the typical numbers that we have. And of course, you want to relate to know a bit more. You want to relate these energy loss scales to other physical quantities. So in principle, you know that the BDMPS average energy loss, as I said, is proportional to Q hat L squared for a static medium. And Q hat, as I said, it's a measure of your particle density. Okay, so there is some expansion due to the cooling, longitudinal cooling, but at the end of the day, Q hat should be related to what I call here this particle density. And if you remember at the very beginning of the talk, I mentioned that we can guess this particle density using data, using the Bjorken estimate and data from the number of particles per unit rapidity. Of course, over some volume here, which is related to the transverse area of your two colliding pancakes. So in principle, all the average energy loss is proportional to some particle density, the particle measurement that you have in data, times some medium length L to some power. I said to some power because in a static medium you expect 2, but because of the expansion you expect in the end 2 minus alpha. So let's be again very agnostic and say, okay, let me plot all the data, all these energy loss processes as a function of dn and L, and let's assume that it has this simple form with a 2-parameter fit. So K in principle can be computed if you know what is the particle density and so on, has some expression. And beta, as I said, well, maybe it should be close to 1 because in the Glauber model, you expect alpha is 1, so 2 minus alpha should be close to 1. And all the things that you cannot really measure, like L, the length and the transverse size, is taken from a geometrical model, a Glauber model. And this is the result that we obtained with my student Guillaume. And you see that all these energy loss scales again very nicely as a function of that scaling variable. So it's nice to see the scaling, and it's nice to see the numbers that we get for the 2 parameters because we get beta equals 1, typically with some uncertainty coming from our theoretical prejudice or the experimental uncertainty here. But okay, it's nice to see that not only we have the scaling on our array, but also we understand the scales that we were fitted a bit agnostically, say, in the first part of that study. So, and the number of the K is also quite nicely understood, even though it's proportional to alpha s to the cubic power. So it's hard to evaluate theoretically, but we're in the ballpark of what we could expect. Okay, so things looks quite nice and simple for hadrons. Now, what about jets? So I had this very simple model with array that was going to 1 at large PT, and you see that when you measure jets instead of hadrons, then you start to see things which are very different. These are atlas data, and you see that array even at PT is almost 1 TeV here, and you see that RA is 0.6. So there's still quite some suppression, and it's rather flat. While for hadrons, you saw some nice slopes. So clearly jets do not behave the same way as hadrons, and it's not a surprise after all, because a jet is not a particle. A jet is a collection of particles that you would construct through a jet algorithm. Of course, it's a good proxy for an initial pattern that has experienced some soft-gun radiation, but it's not a particle. So the energy loss of a jet, of a collection of particles, is in principle a different function of, say, the parametric, has a different parametric dependence than the single pattern energy loss. So maybe these data seem to indicate that as well. So this triggered a lot of developments, as I said, on the theoretical side. So some people went to Monte Carlo generators for heavy-end collisions. I mentioned Joule and Pythia, CAT, trying really to model the full evolution of the medium with all the many particles that act coherently in a medium. There are some other calculations in simplified cases, but which you can compute analytically using PQCD. As I said, the regular radiation of an antenna of a two-particle state, trying to go beyond this single particle energy loss. And just to finish, I mentioned some data which I really like by the Atlas collaboration, in which they start to look inside the jet. So when you look inside the jet, if you identify two subjets in your experiments, you see that, well, they are very, very close to each other. They will have this suppression, and it makes sense because the medium would not resolve these two almost collinear jets. So it's just as one jet energy loss. While the two jets are a bit separated, and the medium will see both subjets. And the price to pay is that both jets will lose some energy, and you could expect some stronger suppression. And it's supported by some analytical calculation. And I think it's just an example of where we're going now, and there are many more measurements that await. Okay, so I was already very, very long. So just to summarize, so okay, this is very complex, and because it's really many-body QCD, but we can study quark-gluon plasma, and thanks to the data, thanks to the theorists, and thanks to the exchanges between data and theory, we start to have a clear picture of what's going on with a medium which has very low viscosity and with a very strong stopping power. And of course, many things can be learned, also not doing heavy-end collisions, but a collision on a proton and a nucleus. It seems simpler, but you will see that there are many fun also looking at those collisions, and it will be really the topic of next week talk, in which I will discuss again energy loss, but in cold nuclear matter, and you will see the differences. That's all. So I would happy to answer your question and to discuss with all of you.
Super. So thank you very much for a really nice talk. I think this is just a tremendous survey of the field, a great introduction, and then some interesting details of your bottom-up phenomenological model of RA. So with that, are there questions that folks have for Francois? Yes, please go ahead.
Yeah, there was a plot you showed with this beta coefficient where you plotted some late collisions and xenon collisions. Yeah, that one. Okay, the next slide, I think two slides, the next one, that one. So at high DN, I see that like the uncertainty on the 5 TeV late collisions is quite large. Like, what contributes to that?
You're asking why these uncertainty are large here?
Those ones that, yeah, those ones.
On these, let me see if I can answer that. It's difficult to say. I don't know if these are that large uncertainties here. This is more central collisions as compared to say you have also some lead data here, the same system but in peripheral. No, in principle, and maybe in principle in central collisions you have really you go even to lower RA that you can see here. So it's hard. It's really hard to say from the uncertainty of RAA how it translates into the uncertainty on our parameter. But I would say that maybe it's just a visual artifact that here these are the larger scales. So since it's a linear scale, it seems that we have very, very large uncertainty. Well, here we have very small uncertainty, but if you look at the relative error, maybe it's not that large. I know that we distinguish between statistical error and systematic error. So maybe it's part of the reason. We really try to say that what happens, we really try to be careful in fitting the data on the normalization. And let me see, how would that go? No, I really can't really tell you. Maybe my student would answer that better than me because he was really into that fitting thing. I can't really tell you why these seem a bit larger. That's your question. But I hope that you got the picture that we fit RAA with a single curve here. And we try to change a little bit all our some assumptions here, trying to get some fitting on the on our error, especially for the area, for the length, because these are not really measurable. So since we want to have something which is very data driven, but we have some theoretical prejudices here on these values, but this epsilon bar in principle is directly related to the errors of the data.
Is it maybe that this just occurred to me that maybe for the largest epsilon bar you have the largest suppression, and then you become a little bit sort of the larger the suppression, the less sensitive you are to the epsilon bar. You sort of need a lot more oomph to get suppressed further. And that maybe that leads you to the larger the uncertainties?
It could be, it could very well be. I know that at very, very low PT, sometimes we see a deviation here. I show only the data above 10 GB, and which we have a nice scaling. But what is even more interesting, and we have that in my earlier paper, is that we start to see that if you start to add some data at a bit different PT, where the array is becoming very, very small in general. You start to see some deviations from the scaling. So could it happen that when we meet, I don't know whether the model is a bit less effective in reproducing the very low PT, low RA. It's so simple that we don't do a full geometrical average. We just say, okay, loses some energy. While if you do really something nicer in the sense that you integrate over all the volume and so on, you would have some RA which is a bit larger than what we could expect here. RA goes to 0 at very low PT in our model, which is not really physical. But I don't know if that translates into that error bar. Interesting.
Super. Other questions? Yeah, Cole.
I just want to ask, you said earlier, when you talked about formation time, you said that the formation time, which contributes to average energy loss, goes like L, which seems a little strange to me because I think formation time scales like 1/E. So is there no energy dependence, and what formation time is important for the average energy loss? I think it was a couple slides back.
Sure. So as I said, indeed, I mean, the gluon formation time is proportional to the gluon energy over the K-perp squared. K-perp squared will be given by really the risk scattering process. So it will be typically given by Q hat times the medium length, or more generally Q hat times the formation time. So which gives you an idea on that if you replace this by Q hat times the formation time, then you have that the formation time is goes like the square root of omega over Q hat. So there is some energy dependence, and this is what you see here. So when you plug this L over TF, which is really the number of radiators, really the number of effective scattering centers, if you wish, this term has some energy dependence, because precisely of what I said, that the formation time should be should scale like square root over omega over Q hat. So it has some energy dependence, and this is why you have some as compared to the independent pictures, a better Heidler, you have some 1 over square root of omega dependence, and then you have even some stronger dependence here, and the average energy loss is when you integrate over all that times the you integrate that spectrum to get this something which goes like this. So you take into account the fact that the medium-induced gluon spectrum varies with omega because of the variation of omega. But when you integrate that, maybe you would get a log here because it goes like 1 over omega. But here I give you some rough estimates at leading logs accuracy. But in principle, you're right that if you integrate that for 1 over omega, you would have maybe some log of the energy. And actually, this is a very important observation because it is independent of the energy or up to log accuracy. Maybe it has a loggy dependence. And this introduces very well what I'm going to say next week, in which I'm going to argue that for the LPM energy loss, it's almost independent of the pattern energy. But for fully current energy loss, which is another regime, it is proportional to the energy. Because we do not expect this big drop here, but something more constant at large omega. So if you have something constant, then you integrate all the way up to the pattern energy here, and you get some energy dependence really proportional to E is a very key observation as compared to here, which you have maybe a logarithmic energy dependence. I don't know if that answers your question.
But I guess I think Cole and I often think about K-perp being determined by the initial emission, and that there's a sort of a K-perp max that scales with the energy. And I think so when one says that K-perp goes like Q hat times some length scale, then one is thinking that basically the gluon is emitted collinearly, and then its K-perp is picked up from rescatterings within the medium.
Yes, okay. I got your point. Well, if you're right that in principle, well, there are two things that we should separate: DGLAP radiation and medium-induced gluon radiation. And I think this is key because when you discuss initial state radiation or even final state radiation for your jet, you have some DGLAP radiation, so which will be put in the evolution of the PDFs or the fragmentation functions, and this indeed can you have a different scaling here. You have K-perp can be as large as E in principle, and it should scale actually like E. But this is vacuum radiation. This is really DGLAP, and you have of course DGLAP in heavy collisions, obviously, and you have it in PP. But when you construct the medium-induced gluon radiation, it's really the difference between the radiation in heavy collisions minus that in PP collisions. And this piece of the DGLAP radiation would cancel exactly, because it's really very, very long before the medium and long after the medium. And so this piece would really cancel. So you're right that in that case, the gluon radiation of DGLAP is very different, and there is no Q hat. There is it has to scale like E. But if you look at the induced gluon radiation, then there's no more declap. Except next week, you will see that sometimes when the things become even more complicated. But for say purely initial state radiation or purely final state radiation, take DIS for final state radiation. You would have some declap if you produce a quark in DIS. There is some declap of say the fragmentation functions if you measure hadrons in the end. But it will be the same in EP and in EA. Then there is this induced part, really the medium dependent part, which will depend on Q hat. And in that case, the typical transverse momentum maximal acquired for those induced gluons, which are radiated, is bounded by Q hat L. Does it make sense? Did you get the point?
I think so. I mean, I think it's the very big conceptual difference between the sort of expanding around the very, very large scattering limit versus the very, very few scattering limit. So I think when we think about things in terms of a very thin plasma, then the rescatterings, while you may have LPM suppression, it's much more DGLAP-like in terms of the phase space that one can emit the radiation into than I think the BDMPS type conceptualization of the problem leads one to conclude.
It could be. I know that this interpretation is maybe a bit indeed formalism dependent. I know that also in the higher twist formalisms, it's hard to distinguish really what we call the hard process and the induced gluon radiation. So in the picture that I have, it's a bit separated. Maybe it's a bit ad hoc in a sense. It's just an approximation. But yes, I would tend to separate the hard process, a very large Q, much larger than lambda QCD or T or whatever, and really the medium induced part. So we can argue whether it makes sense to compute the induced gluon spectrum the way it is. I mean, just looking at the difference between say PA and PP or AA and PP, but still physically, I mean, if the typical emission time is very, very large as compared to the time for the hard process needs some time, what we call the UFI time. If there is radiation well before or well after that, it should not be medium dependent in principle, except what I'm going to say next week. But and if it's not, if it's independent of the medium, then in the induced prescription of doing induced gluon spectrum in say in A minus that in PP, it should cancel. So all what is left is something which depends on Q hat. And then the scale, natural scale, is Q at L.
Cool. I think.
Yeah.
No, please go ahead.
Well, at the beginning of the talk, I think you gave a value for viscosity, eta over S. I think it was plus in 0.2 plus minus 0.1.
Right, something like that. Yes.
Okay, so that uncertainty is quite high. It's 50% error. Why is it so high?
So, well, first of all, I'm not at all responsible for that. So you should ask all the hydrodynamics practitioners, but I would agree with them. Well, first because here, so first of all, the data itself, how you compute things, how you extract V2, for instance, and how you get rid of non-flow effects is something very very subtle. As I said, you can really do 2 particle cumulants, 4, 6, 8 particle cumulants. So you see that even the data itself has some uncertainty, some systematic uncertainty, I would say, and but on the theory side as well. maybe the biggest uncertainty on the theory side is related to the initial conditions. So in hydro, you need to have some equation of state, but you need also to have some initial conditions. And depending on what you assume for the initial condition, you have some different results. So here on that plot, you see Glauber. Glauber, they assume some random generations of nucleon positions, and then they do their calculation, but it's done at, say, at the nucleonic scale, so fluctuations of the positions of nucleons. Now, if you said that everything happens really on the partonic side, then you can compute the fluctuations of the partonic fields, and you have some different eccentricities in that case. And since V2 is very sensitive to the eccentricity of your collision here, that you see here, well, the amount of fluctuations is really different. So I think I have it in the backup, but in that Glauber picture here, V2 as a function of PT, if they repeat their calculation with, say, partonic fluctuations, all the curves go up, okay? So you can guess that from what you see here that, of course, the more viscous, the less V2. So if naturally, because of the fluctuations, all the curves are larger in V2, they have to compensate if they want to reproduce the data, and let's say that eta over S is a free parameter, they have to have a larger eta over S. So I think mostly the uncertainty is related to the initial conditions, I would say, and to some extent to the data. Now, if it's big or not, yes, you can say it's a 15%, so it's huge, but I would say it's not that important, in the sense that, of course, it's maybe a bit dependent on the initial conditions and all that, but after all, it's a small number. Even if it's 0.1 or 0.3, say, it's a small number. So I would not say, oh, it's exactly 1/4 pi. I don't really care. Maybe it's just 2 or 3 times 1/4 pi, but it's not 1 or it's not 10 in that sense. So if we had really something which is more like plasma, like a gas of weakly interacting particles, you have eta over S in principle that goes to infinity. So something in the PQCD picture with a very small interaction strength, eta over S is it's a number much larger than 1. And here you can vary, you can play a little bit, and you can be conservative, because in any case it's much smaller than 1.
Okay. Yeah, that makes sense. Thanks.
Super. Any further questions from the audience? As a chair, I have a question, perhaps a provocative question.
Sure, go ahead.
So you showed this beautiful scaling with the RAA as a function of your scaling parameter, this curve with basically all the data falling on this curve. I mean, really, yeah, perfect, really impressive. I'm you started off talking about the Bjorkane scaling, so I'm tempted to think of this as the Arleo scaling. So Bjorkane scaling says we really learned something, right? That it's really partons inside the hadrons, and that we have asymptotic freedom. So what is the physics that you think we extract from this RAA? Because I think the message I got from leading up to this was very simple ingredients, which is good, right? So you've got the power loss scaling, you've got the energy loss that looks sort of fractional energy loss that you can approximate by an exponential. So, is there something very deep beyond that we're learning from this?
I would say that we learned that it's very simple in the sense that if this is a very, very naive model. I mean, I have many great colleagues that do very fancy calculations with hydro and so on, and it's important to do that as well. Here, it's just another way really to put things. But if you really go to the easiest thing, and again, also many people are brave enough to go to low PT, and I don't go there. So, but at least at very large PT, say above 10 GeV, things becomes very simple. And this is what is implied by the scaling. And so if it's universal, it means that there is only one single process. You can forget about all the other processes, to be provocative as well on my side, because nothing really counts. I mean, of course, there are many other effects, but maybe they are subleading, at least again above 10 GeV. And we are left with one process which can be modeled simply. Now, of course, what we could object in that picture is, okay, we have this nice scaling, but epsilon is well, we don't really know, it's just fitting. But this is what I also like here, that okay, not only it scales, but the energy scales themselves, the fit parameters are natural, in the sense that they scale nicely, and with beta, which is also with a very large beta, which is close to 1, as we would expect. So this says that maybe there's only one physical process for radiated energy loss, and this physical process is really what we could expect in PQCD. So I would say that, again, to be provocative, it excludes maybe energy loss at strong coupling, which says that, okay, maybe the parametric dependence is L to the cubic and so on. And after all, if we can refine things, we can embed that into some sophisticated hydro, but there's even no need, in a sense, again, to be provocative. There is really no need if it's that simple. And what is interesting is when we move to jets, it's too simple, it's too naive. But maybe for hadrons are the best proxies for partons, in the sense that in PP collisions, we often say that a jet is the best proxy for a parton, and it's true. In the high energy limit, the jet would be a pencil-like, exactly like the initial parton. But when you look at parton energy loss, if you want to study that, maybe go for large PT hadrons and extract the parameters, and you would get something maybe close to that. While for jets, it's what makes the field so exciting, and why in hard probes we had so many talks on jets, that okay, there's a lot of going on trying to understand very complicated things here. But I always like when things are simpler. This is where I can contribute, at least.
Okay, so one tricky follow-up question. So I liked how you were thinking about how this might break. So you went to lower PT and then the scaling fell off. So that's very good. So, and we expect that, and that's great. So what about when things systems become small? So very peripheral, or maybe even RPA, to be very, very tantalizing.
Now you're asking my question.
Yeah, it's difficult. Yes, can I apply these techniques for a super mini plasma? For peripheral collisions, I have to be clear here. So in my first paper some 5-6 years ago, I said that RAA, well, you don't have data, well, you don't really, see the data, but in the very peripheral bins, the RA was flat but below 1. And I wrote in my paper that I don't understand that. It's something else. And at least in these very powerful collisions, and RA was not only flat, but not 1, which was a bit surprising. And then I found that there is some bias, and geometrical bias, how you classify your centrality bins and so on. So with my student Guillaume, and he really looked into that. So he said, okay, these data, very powerful data, so 70-90%, they have to be corrected for this bias. And when you correct that, it goes all the way up to 1. So because of this correction, we were able to include these, but even I was not very confident, at least 5-6 years ago, to include that, because it seems a bit different. Now, just because of heavy ion collisions, very, very powerful, and then you start to hit some geometrical bias. Now, in really in PA, which is your question. So I don't know. I think it will work, but we want to have some high PD particles, and high multiplicity PA collision. Because for I think you would agree with me that for minimum bias PA collision, take just a PA collision without any bias on your particle multiplicity, it scales, I mean, almost like PP up to the nuclear PDFs and so on, which I'm going to discuss next week. But there's no hot medium produced in a minimum bias PA collision. If you start to trigger on high multiplicity PA collision, if you start to trigger on a high multiplicity PP collision, you start to see some QGP-like behavior. So I wonder, do we have some data on RPA as a function of PT, so even large PT, with large multiplicity? If we do have that, I would expect that it follows the same trend. And I know that my student Guillaume was interested into that, and he tried to make some estimate on what would be. So now that everything is fixed here in our scaling here fit. So in principle, K and everything is fixed. So he said, okay, now if I know what is my D and DY in PA, which can be large in some really non-minimal bias PA collision. So he was able to compute epsilon, and because everything is fixed by epsilon, so you just look at the number here. You put some a perp L, and he got some, say maybe 1 GeV. I forgot which scale it was, and so he was able to compute the RPA in large multiplicity, and he found some 10% effect or so on. I think we have we mentioned this in the paper, but so yes, in principle, I would expect some effects, but we look at high PT particles and we want PA collisions with high multiplicity. With minimum bias PA collision, multiplicity is quite small here. So epsilon is too small and R should be 1. Don't know if you agree with that.
No, that's great. Yeah, that's exactly what I think we think about is the high multiplicity collisions, and does one see signs of some final state effects? Yeah.
Yes. I should go back to the paper for the numbers. I think we had some 10% effect. It's a challenge, but it would be fun because there's in principle, yes. Why we don't see any jet quenching in high multiplicity PA collisions, but I don't think we have data yet, except minimum bias.
I think there's some. Maybe we'll have a bit of a because
okay, could be.
Good. Any last desperate questions? No, super. So Francois, thank you so much for taking the time.
Cool. Yes, it was nice.
Yeah.
I enjoyed it very much. So thank you again for the invitation, and I will work on my talk for next week. Well, I will discuss some other things. But related.
Really looking forward. Super. All right. Take care, Francois. Have a great weekend.
See you next week. Bon weekend.